So there's some confusion on doing these titration types of problems and having buffers where you add an acid or a base, a strong acid or a strong base to them. So one of the keys is whenever you have a strong acid with a strong or weak base, you need to do an initial change final box, which is just really doing a limiting reactant problem. But often the trouble is figuring out what reaction you need. Now for these problems, for A, you should be able to do that. I'm not going to go through that. For part B, I will go through that right now. We're going to start with our ICF, and we have HCl, which is, we're just going to look at the H+, because we don't care about the chloride. And we have also NH3. That goes to completion to make NH4+. Now we have 40 mils of 0.1 molar NH3, 20 mils of 0.2 molar HCl. For our ICF, I'm just going to do moles. So H plus moles for H plus will be 0.020 liters times 0.2 moles per liter, which is 0.004 moles. So we put a 0.004 here. And the NH3, we have 0.040 liters and 0.1 moles per liter, which is 0.004 moles. Oh, we get the same amount, 0.004. And we don't have any ammonium in the beginning. On our change row, we're looking for a limiting reactant. And when we look at these two species, we see we have the same amount, so neither is limiting. They're both going to go down by 0.004. And that means the NH4 is going to go up by 0.004. And at the end, we have no H+, we have no ammonia, we have only NH4+. And these are moles. When we do an ice box, we need to have molarity. So I'm going to have to divide that by the total volume. My total volume is 40 milliliters and 20 milliliters. So the total volume is 60 milliliters. And the molarity or concentration of NH4 plus is going to be 0.004 moles over 0.060 liters, which is, that is 0.0667 molar. Now at this point, we need to go through an ice box because that's what we do. We get the final row and we'll use an ice box. When you do an ice box, you need an equilibrium reaction. All we have left is a weak acid. So whenever you have a weak acid, you always add water to it, and weak acids should produce H3O+, because they should produce an acid, and the conjugate base of the weak acid. And you put in what we had initially, 0.0667. We don't care about the water, 0, ICE minus X, 0.0667 minus X, 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 X. Oh, we need the Ka. So we had the Kb. It was in your notes from earlier, from a few days ago. We know that the Kb for NH3 is 1.8 times 10 to the minus 5. Therefore, the Ka for NH4 plus is the Kb divided by 10 to the minus 14. And that is I'm pretty sure it's 5.6 times 10 to the minus 10. Let me check that. All right, that was good. That was correct. So now I'll plug in my equilibrium row. And I have my Ka, 5.6 times 10 to the minus 10 is x squared over 0.0667 minus x. And we're going to assume x is small, so we get rid of that. And if we solve this equation, this is 0.0667, we're going to solve that equation for x, and we get x equals 6.1 times 10 to the minus 6. And the question asked, what were we asked? Calculate the pH. So to get the pH, we're just going to take the log of this number, log of the answer. We get 5.21. There we go. Okay, new problem. Now, do we have our original solution? Calculate the pH of the solution that results when 40 mils of 0.1 molar ammonia is mixed with 20 mils of 0.2 molar NH4Cl. You have to realize we only care about the NH4+. So again, we will, here we have to do a dilution because we're not doing an ICF. Why aren't I doing an ICF here? I've got NH4Cl and I'm mixing that with ammonia. There's no strong acid or base here. Nothing strong present at all. And if I have nothing strong present, I don't need to worry about doing an ICF. I just go straight to an ICE. But I have to do a dilution. So I have 40 mils of 0.1 molar NH3 and 20 mils of 0.2 molar NH4+. So 40 milliliters. I'm going to do an MIVI equals MFVF for both components. I have 40 mils of 0.1 molar NH3, MIVI, and my final volume, I have to add my 20 mils to the 40 mils. My final volume is 60 milliliters, MF. And so the molarity for the NH3 is going to be 2/3 of 0.1, which is 0.0667 molar NH3. And I also needed to do a dilution for this one right here. This one I have 20 milliliters of 0.2 molar NH4+, MIVI, and the final volume, we added the ammonia solution and the ammonium solution together, 60 mils total, MF. So the molarity of the ammonium is going to be, let's see, 1/3 of 0.2. Oh, it's also 0.0667 molar, but that's NH4+. So now I need an icebox. I had a Ka and I have my Kb. It really doesn't matter which reaction you use as long as you use the correct version of your K, your equilibrium constant. So I'll do my ammonia reaction with my Ka. So I have ammonia. When you have a weak chemical, you don't put two weaks together. You add a weak to water. When I say a weak chemical, a weak acid or a weak base. The weak acid or the weak base plus water will make the conjugate. So I had a weak base. I make the conjugate weak acid. And I will be left also with hydroxide. Now I put in my ICE initial concentrations. The NH3 right here is 0.0667 molar. And the NH4+ right here, look at that, it's also 0.0667 molar. It's hard to read that, I know, sorry. We don't worry about the waters, hydroxide is 0. Change, minus x, 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 0.0667 minus x, 0.0667 plus x, x. Okay, so my ending concentration, actually this one you should have been able to do. This is straightforward. This was on your test. We have Kb times 10 to the minus 5 is x times 0.0667 over, so that was x times the 0.0667 plus x, but I'm going to ignore this plus x because we're assuming x is small. We assume that when the Ka or the Kb is small, that means x is very small. And we need to divide by reactants. We're going to again assume x is very small, so we're just going to divide by 0.0667. Oh, beautiful. These cancel out, and x is 1.8 times 10 to the minus 5. and the pOH is 4.74, which means we're running out of space here. Sorry about that. The pH is 14 minus that, which would be 9.26. There we go. Oh, did I not put that as the correct answer? I don't remember what I had on your sheets. Okay, so now, part D, learning Henderson-Hasselbalch. pH is pKa plus log of HA, log of A minus over HA. Okay, so now there's this, actually a much easier way to do these problems, Henderson-Hasselbalch. So we're going to have pH is pKa, which is negative log of the Ka. We're going to do this for part C of number 1. The Ka was 5.6 times 10 to the minus 10. pK is just negative log of that, plus the log of A minus, right, oh no, A minus was here, that's our base, 0.0667 over HA, here's my acid, HA just means acid, A minus means base, here's my acid concentration, 0.0667, and when I solve this I get 9.26. The Henderson-Hasselbalch equation comes directly from solving this equation right here. If you actually take the log of both sides of that equation, you get the Henderson-Hasselbalch equation, which is why you get the same pH. So, if you ever are doing an icebox where you have both a weak base and a weak acid present, you don't even need to do an icebox, you just go straight to Henderson-Hasselbalch. And when we have a test on all of this, you will be given the Henderson-Hasselbalch equation. You were given that on your last test, but most of you didn't know how to use it yet, which is okay because that was an extra credit. No, not that problem. There was another problem that was an extra credit problem. Okay, so anytime that you have both weak base and its conjugate weak acid, you can use Henderson-Hasselbalch. All right, new problem. So above for solution, we've got, all we care about here is the HCO3 minus and the CO3 2 minus. Okay, we've got moles of potassium hydroxide, we've got molarities. Oh, I was going to say, I need my volume. It's not going to make any sense if I don't have volume. What is the pH of the resulting solution? Well, first I'm going to do an ICF. You should recognize I'm adding hydroxide, and hydroxides react with weak acids. And of these two, I sure hope you recognize this would be your weak acid. So HCO3 minus, they react completely to make CO3 2 minus and water. Now in my ICF, I'm just going to do moles. So I've got to calculate my moles of carbonate and my moles of bicarbonate or hydrogen carbonate. I'm going to pause this and just calculate that. Okay, in case you're wondering, I did the calculations on the left here. I just used my molarities and the volume for the bicarbonate to get the bicarbonate moles right here. And I'll put those right here. And I use my molarity and my volume to get my moles of carbonate, 0.0538. And I'm told, oh, I don't have to calculate anything for the hydroxide, yay! I have 0.0464 moles of potassium hydroxide, or hydroxide. I don't care about the potassium, it's a neutral ion. We learned all about identifying our neutral ions in the last chapter so that we could figure out what we cared about in these acid-base reactions. Now I need to find my limiting reactant. I have a 1-to-1 ratio, so the limiting reactant is just whichever of these is smaller. So everything that is reacting is going to go down by 0.0464, down by 0.0464. Products are going to go up by 0.0464. I don't care about my water. My final row, 0, oh, that's nice, 0.0400. That worked out quite nicely. Oh, this one does too. Look at that. Oh, no, it doesn't. 0.0538. I thought this was going to come out nicely. It's not so nice. It's sort of nice. 0.1022. Okay, so now notice I have my weak base and my weak acid present. I would suggest, I told you in this problem, go through and do an ice box, do an ICF and then an ice. We're going to do the ice box, and then I'm going to show you Henderson-Hasselbalch in a moment to show you don't actually have to do an ice box. We were given the Ka of bicarbonate. So let's do an acid reaction so we don't have to calculate the Kb, like why calculate a Kb if we don't have to? When you have both the acid and base present, you could do either the Ka or the Kb, the acid or the base reaction. Always add water to your weak acid or weak base. This is a weak acid, and weak acids lose their H pluses to become their conjugate bases, and we get H3O plus. It's an acid, it's producing H3O plus. Oh, and we had moles, we need molarity. ICE. Okay, what was our volume? Oh, our volume is right here. 225 milliliters, or 0.225 liters. So this will be 0.04 over 0.225. Water I don't care about. This will be 0.1. I'm just going to keep it 0.100 because it's really just 3 sig figs over 0.225. And the H3O plus is starting out at 0. You don't know which way this goes, and it doesn't actually matter because we're going to assume x is small. X. Actually, the way we wrote it, we have to go to the right to produce the H3O plus. Okay, I'm going to calculate those numbers. Okay, and now I just do my Ka as products over reactants. My Ka is 4.7 times 10 to the minus 11. This is going to be x times 0.444 over 0.178. I'm ignoring the minus x's and the plus x's because we're assuming since Ka is so small, x, the change amount, is going to be really small because we're not going to get a whole lot of product because K is so small. So x is small compared to any real number, small compared to 0.14, small compared to 0.178. And now we find x is 1.88 times 10 to the minus 11, and the pH is 10.7 right there. Now, let's use Henderson-Hasselbalch and see how it works. pH is pKa plus log A minus over HA, which is, where's our pKa? Negative log of 4.7 times 10 to the minus 11 plus the log of 0.444 over 0.178, which is 10.7. We get the same answer. Look at that. Henderson-Hasselbalch. You have to be very careful with this little negative sign here and making sure you plug in everything correctly, but if you do it, you're good. Okay, number 3, I'm not going to solve for you. You should be able to do number 3. And I'm going to give you one other problem to do, and that will be the end of your homework tonight. Okay, I have the other problems. This is problem 3, problem 4, problem 5. I'm going to put up the solutions. I'm not going to record the solutions. So you are supposed to do these on your own. Do not just copy the solutions. I'm not going to work through them, but you should do, pause to copy this down. Or no, you should have this already written down. It's whatever. It's on Edline. But I will go through all the solutions. You can copy them from here, but you should try to do it on your own. And then you can copy them if you are just totally stuck. Or look at them and then try it on your own. But I'm not going to record the whole thing. Okay, there's the answer to number 3. I'm going to just move on to the other 2 and show you the answers to those as well. Here's number 4, and just real quick, I calculated moles for the I row. And then to do Henderson-Hasselbalch, you have to make sure you go back to molarity, or to do an icebox, you should use molarity. Actually, I don't want to explain why you could use moles and get the same number, but you should always use molarity. Even though for Henderson-Hasselbalch, you actually, the liters cancel in this division here, you should still do molarity. Okay, and now I'll go through the last one. Okay, and here's your solution for the last one. Again, I used moles in the I row, and then you have to use your F row to get molarity. Always divide by the total volume to get molarity, and that's it.